In the previous lecture, we have seen some theory about integers and how to think about integer arithmetic. Now we're going to see some of the methods how you can solve constraints in linear integer arithmetic and quantifier free. In this case, we will sometimes introduce quantifiers and we will say, okay, I want to eliminate exist x, and by eliminating existential quantifier, I will be solving constraints. So I will not be assuming there will be any other universal quantifier, only existential quantification. Then the problem reduced to the quantifier free fragment. So we'll look at three methods, which is first is the simplex method, and we will introduce an idea of cuts and then see if you those together, how can I solve an integer constraint. Then I look at the Cooper's method in detail, and I will hint about this third method, omega test method, which I will not go into detail, but give you some hints how can omega test method can be viewed as some sort of optimization over the Cooper's method. So let's look at our first method, which is called Gomery cut. So what is a Gomery cut? It depends on the idea of cuts. So what is a cuts? Okay, so once you have linear constraints, they form a polyhedron where the satisfying solutions lies, and there are some corners which are not integral, and simplex by definition look for corners and gives you solutions at the corners. So if the corner is not integral, it is not going to give you the integer solution. So what you want is to cut out this the side corners where you have a non-integral solutions, and this is called cuts. So how the procedure moves is that, let's suppose simplex give you this point. Okay, this is a corner and which is not an integral point. Whatever method that produces cuts, so first it does is try to find a plane which contains the polyhedron, and then you move this cut towards the polyhedron such that no integral solution gets is removed from your set, so satisfying set, and therefore you have a new constraint. Okay? And using this new constraints, you strengthen your constraint system, and then you solve again, and eventually you will cut it enough such that you will find a integral satisfying set. So remember that we had the simplex, and the simplex had this normal form, and in which you have ax equals to 0, and every variable has bounds, which is lower bound or upper bound. In the following presentation, we will assume that every variable has bounds, at least one of the bound is present, and all the bounds are integral. Okay? So that's another assumption. The Gomery cut chips away in non-integral parts of the solution space, as I have described, and how it does it is that it runs simplex, okay, and if all variables are rationals, and finds an assignment B. If V is integral, then we return the answer. If V is not an integral, then for some basic variable Vi is not integer, right? Then add a constraint to eliminate the neighboring non-integer space around that point. So since all the bounds are said to be integral, therefore you will always, non-basic variables will always get an integral value. However, if their basic variables may get non-integral value because they are computed from the values of the non-basic variables. Let us suppose the ith variable xi was the one which did not have integer value after assigning the values to non-basic variables. So this row is the problem row, right? So the calculation is producing a non-integer value. So you remember that this equality has to satisfy by every solution of our problem. So without loss of generality, we assume all upper bounds are active at the non-basic variables. So these are the non-basic variables, and we assume that everything is active at the upper bound. Yeah? And we can similarly analyze the lower bound case. We will not cover here, but that will be left as an exercise. So everything is at the upper bound. So then you write the upper bound value, and that gives you the value of xi at that corner. Okay. Now what do? I will take this equation and this equation and subtract one from another. And if I do that, I will obtain this equation. In this equation, you can see that if at the position, if xi takes the value of vxi, okay, and xj's take the value of uj, then this is whole sum turn out to be 0. You know, this is an important thing to notice. And then we are going to use this equation to finally learn a cut equation. Okay? And that's what we get. Yeah, so what we do, we will take the equation and just take the take every coefficient, every number there appearing, and just take the fractional part of the coefficient. And note that the fractional part of xi was 1, and you take the fractional part, it will become 0, so it will not appear. And then we'll say it's greater than equal. This linear inequality is very interesting. This inequality allows us to separate the non-integral point, which is our current solution, from all the other possible integral solutions. So let's see how it does it. Okay? So first we will say the current solution does not satisfy the above. Okay? So this is why, because vxi is fraction, has a fraction value, so therefore it's greater than 0 value. Here every current assignment, all the non-basic variables are hitting the upper bound, so this value is 0, so therefore whole sum is 0. So therefore this linear inequality does not succeed at the current assignment. And we will show you that any integral value must satisfy these inequalities. Why? Any integral solution you can choose, okay, of the equations must be smaller than uj, right? So the uj is integral, this guy is integral, right? And this is smaller, so this is a positive integer, right? So it's a positive greater than or equal to non-negative. This is a non-negative integer. Therefore, if you multiply it with a fractional value, you will get something which is greater than or equal to 0. Now let us look at another aspect of this. We are trying to put the integral values x in this equation, right? So xi is integral, xj is integral, so this guy is integral, this guy is integral. If I try to take a fraction of the whole thing, then I will get this equation. You take the fraction here, and then you can also take the fraction of these coefficients only. Okay, so all the integral parts will just imply with this integral, and they will not help you generating fractions. So this is basically gives you the fractional part of this equation, this right hand side. Now you got this equality. Now you can see that this is a positive number. We know that this is a positive number because of this guy. Okay, since this is a non-negative number, what you can do is you can say that its a fraction must be smaller than it itself, right? So you can basically write this equation. So therefore any integer should satisfy this linear inequality, and current assignment does not satisfy this linear inequality. Therefore this linear inequality separates the integral solutions of your problem than the current non-integral solution, and this can be used as a cut in your problem. What we do, we introduce this new inequality in your simplex, introduce new slack variable, what are the process you know, and now this current assignment is gone from the solution, and then you need to do some pivoting, and then you find to another corner. If it's not integral, then you keep adding more and more cuts, or at some point of time eventually you get a corner that is integral. So now let's look at one more case which we may have. This is when one of the non-basic variables does not have any bound. In that case, our method will not really work as I have presented, and there are other ways you can make it work, but let's look at another idea that can solve our problem. Okay, what do? We can introduce this kind of case splits. We can create two separate problems, in which one we say that xi should be less than equal to the smaller one smaller integer value, and the other one is one bigger integer value. Let's look at the case. Let's suppose the current assignment of vxi is 2.3. So what you can do, you create a problem where xi added constraints are vxi is less than equal to 2, and another problem you create in which xi is equal to greater than equal to 3, and you solve these two separate problems. If any one of them become satisfiable, you have a solution, otherwise you have unsatisfiability. This creates a case split, and then it's called branch and bound method, and it doesn't have to be applied in place of Gomery cat. You can apply whenever you feel like. So a lot of tools don't use Gomery cat all the time. Sometimes they try to avoid complexity by just implementing branch and bound. Maybe it works. If it doesn't work, they fall back to more complex solutions. There has been many proposed methods which can give you cuts in very different ways. There is still ongoing research how to obtain best cuts for a given problem.